In today's lesson, we are going to look at distributive property. So it's kind of combining or looking at similar to some of the previous lessons we've looked at. It will involve collecting like terms. It may involve adding or subtracting polynomials to some degree. You could argue that adding and subtracting polynomials does include distributive property in itself, but at a very basic level. But we'll work through how to distribute the property. So as a warm-up, so I'm at McDonald's getting food after a long day of work. I plan on getting a 2 cheeseburger combo meal as we see here. But I realize that it's a long line at the drive-thru and I'm bored, so I want to come up with an algebraic expression to represent this combo. So algebraically, how can I represent this 2 cheeseburger combo that we see here? Well, I have 2 cheeseburgers, so I know at least I'm going to, oops, I need to get the right color. I know at least I'm going to have 2. Well, 2 of what? Okay, 2 cheeseburgers. How do I represent that algebraically? Well, we can use a variable and say that we have 2c, 2 cheeseburgers. Plus, what else do we have? We have 1 fry, so I can say 1f, and we have 1 pop. You say 1p. So that's our algebraic expression, or the algebraic expression that I came up with to represent the combo. Now you could use different letters. You don't always have to use the letters that match it exactly. Technically you could use x, y, and z if you really wanted to, as long as you clarify or you understand what x, y, and z represent. X represents the cheeseburgers, y represents the fries, z represents the pop, that type of thing. So sometimes using letters that are associated with the item tends to be a little bit easier, not always necessary. So as I'm going through the order, I get a phone call. Oh, everyone at home is hungry, so I need to get a combo meal for my wife and son as well. What would be an algebraic expression to represent this change? Now, there may be multiple ways that you come up with this. Right? You might say, okay, well, I need to have 3 combo meals in total. Well, if I have 3 combo meals, 2 cheeseburgers each, you'd say that's 6 cheeseburgers. Right? Or we might say, well, I have, let's go back to basics, 2 cheeseburgers plus 1 fry plus 1 pop. Oh, well, I got another one, so another 2 cheeseburgers plus 1 fry plus 1 pop. Plus a third one for the son, 1 fry plus 1 pop. In total, we add them all up, we end up with 6 cheeseburgers plus 3 fries plus 3 pops. Is there another way that I could represent this? Or could I represent this in a different way without having to add them all up? Right? What essentially are we doing when we're adding the same thing over and over again? Well, if I'm adding the same thing over and over again, basically I have 3 of the same thing, or I have 3 groups of the same thing. Another thing that we could do is we could say 3 times that 1 combo meal. Right? If I have 3 of something, I can multiply by 3 instead of adding it 3 times. So we should recognize that if I take my combo meal, multiply it by 3, it would give me the same answer of what I did. So how does the distributive property work? How does multiplying this polynomial by a value work? Well, that's what distributive property is. So take that idea, and I want you to create your own ideal combo. Right? So we have a bunch of items here from a fast food restaurant. I want you to create your own ideal combo. Come up with what your ideal combo is and create an algebraic expression for it. Very similar to what we did or for my combo meal, but you're going to be doing it for yourself. And you can create whatever combo meal you want. what I want you to do then is to write out that algebraic expression for that single combo meal, right, for yourself. And imagine then that you're like, you know what, this combo meal is the best combo meal I've had. I want to share this with my friends, or I want to share this with people. How many combo meals are you going to buy? How many people are you going to share this with? Right? Whether it's, maybe you're going to share it with 4 people. You're like, no, 4 people's a lot. I'm just going to share it with my best friend, 2. Or I'm going to share it with my siblings, so I'm going to need 2 of them. Something like that. Come up with how many combo meals you need to buy, or choose a new number other than 1, and come up with an algebraic expression to represent that, or to represent that change. Very similar to what we did. So take some time, try that. If you need to pause the video, you can. But try to come up with an expression, and then an expression for when we have multiple of them. Because that will help you kind of get an idea of what distributive property is. So, hopefully we have a better idea of what the distributive property is. And this is what it looks like algebraically, right, without any numbers or anything. So distributive property is when we are getting rid of the brackets by multiplying everything in the brackets by the term in front. So distributive property is just another way of saying multiplying, or multiplying in a specific scenario. So here we have A, and it's multiplying this bracket, or this polynomial. So this single term is multiplying x, and it's this single term A is multiplying x plus y, that polynomial. So similar to the example we just did with the combo meal, we should see that this A multiplies both parts, or both terms inside that bracket. So this works out to A times x, or ax, and A times y, or ay. So that when we distribute the property, we get rid of the brackets by multiplying everything in the brackets by the term in front of the brackets. So that's what we're going to be looking at today. So let's look at an example that's already done for us. 5 times 4x plus 2 in brackets. So because 5 is multiplying multiple terms, or a polynomial, this 5 has to multiply the 4x, and it has to multiply the 2. So it's multiplying both terms. So again, to apply the distributive property, I must multiply both terms in the bracket by 5, which we see in the second line. And then we simplify it, 10x, or 20x plus 10. So that's the simplified answer. I've expanded or multiplied and then simplified. Let's try to go through some of those examples on our own. So 2 times 5x plus 3. This 2 has to multiply the 5x, and it has to multiply the 3. Right? And that number on the outside, in order to remove the brackets, has to multiply everything. So I'm going to write this out the long way. So 2 times 5x plus 2 times 3. Let's start with the easy one. We know 2 times 3 is 6. 2 times 5x. How does it work when we multiply that? Well, very similar to when we were dealing with our power laws. Focus on the parts that are the same. 2 times 5 is 10. X, there's nothing I can multiply with, so it's still attached. So this works out to 10x plus 6. Do we have any like terms between the 10x and the 6? We do not. So I've simplified it as much as I can. I can't simplify it further. You will have to collect like terms at some point when expanding, so just always be on the lookout for them. If I look at B, minus or negative, and then bracket 3x plus 1. This is where it's similar to the subtracting polynomials. What number is in front? Well, technically in front, we don't see anything. We know there has to be something there because we have the negative. So when we don't see anything there, that's the same thing as saying we have an invisible 1. And I'll just draw it. We know it's invisible because it's not there, but we have an invisible 1. So this negative 1 needs to multiply through to both parts of the bracket. And when we do that, negative 1 times 3x plus negative 1 times 1, we end up with negative 3x minus 1. So all we've done is we've just changed the signs. Went from positive 3x to negative, and from positive 1 to a negative. So we've multiplied through, we were able to drop our brackets, we distributed our property. This is why when we're subtracting polynomials, we have to change the sign in every term in the second bracket. Because we can imagine that negative out front gets applied to every term on the inside. You could think of it as when we're subtracting, well, everything needs to be subtracted, so then you have to apply that to every term. Same idea here, this is just another way to visualize that. Again, there are no like terms in the end, so we simplified it as much as possible. Let's look at a larger example. Here I have two sets of distributive property. So I have 2 times 3y minus 1 in brackets plus 3 times y plus 4. So in order to drop these brackets, I need to multiply all the terms inside the bracket by the number or the term that's attached to it. So this 2, I need to multiply to the 3y and to the negative 1. It doesn't touch any of the other brackets because it's not, that 2 is not attached to it. So I don't multiply anything outside of that bracket by 2, only the terms inside. So that means the 3 is only multiplied to the y and to the 4. So let's go through. 2 times 3y is 6y. 2 times negative 1 is negative 2. Positive 3 times y is positive 3y. Positive 3 times positive 4 is positive 12. Helpful hint, if you're multiplying if you have multiple distributive properties to worry about, for the second one, always make sure to include that sign when you're multiplying into the second set. This will make it easier so you don't need to include brackets again. Right? You could think of it as when we're subtracting polynomials, that negative got carried through to every term. So when you're multiplying a second polynomial, make sure you include the sign in front when you multiply it. That way, when you're about to combine everything, you can just write out your answers as you see it, or as they come up. Now let's look to see if we have any like terms. Well, I have a 6y, and I do have a 3y because they both share a y. I also have a minus 2, which is just a number, and a plus 12. So let's combine those like terms. 6y plus 3y is 9y. Negative 2 plus 12 is positive 10. I've now collected my like terms. I can't simplify it any further, so that's the end of my distributive property and collecting like terms. Now, in all our examples, we've had numbers in front. We could have a situation where we have a variable in front. It doesn't change what we do, but it does require us to involve our power laws. So we do need to be careful, or we do need to make sure we remember them. So this reads as x times, in brackets, x plus 5. So that means in order to simplify, I need to expand or multiply. That x needs to multiply the first x and the second x. So x times x, or you could think of x to the power of 1 times x to the power of 1 plus x times 5. Right, so I'll write this one out in the long way. You don't need to write this step if you're okay or you understand what they multiply to. If it helps, by all means, you can write it. So x to the power of 1 times x to the power of 1. Power multiplied by a power says we add the exponents, or x squared, plus x times 5 gives us 5x, right? There's no power rules there. They just get combined together. Generally speaking, you do want to have the coefficient in front as well. So not x5, usually it's 5x. If I look at it, there are no like terms between them, so I can't add them because x squared is different from x, right? Remember, it's not just the same letter, it's also the same exponent, which in this case, they do not have. One last example, or one last general example, then we'll get into some area questions. So again, this is a little bit more complicated, but again, focus on distributive property for the terms and the specific brackets. So in this case, the minus 2x multiplies the two terms there, and the second one, that x multiplies the three terms in the second bracket. So negative 2x times x, negative 2 just stays the same, x times x becomes x squared, negative 2x times negative 2, negative 2 times negative 2 is positive 4, and the x gets carried along. I've distributed now one bracket. I need to do the second one. So x times x squared gives me x cubed. X times 3x gives me 3x squared, and x times negative 1 gives me minus 1x. Now that I've distributed my property, I can look for collecting like terms. I have a negative 2x squared, and I have a 3x squared, so again x squareds. I have 4x and minus 1x. And in this example, I have a 3x cubed, but there's no other x cubed, which is okay, because you're allowed to have terms that don't have another like term in the expression. It just means it just carries through, it just drops down. You don't collect it with anything. So if I collect my like terms, negative 2x squared plus 3x squared, I get 1x squared. 4x minus 1x is plus 3x, and plus x cubed. That just gets carried down. So again, I'll highlight to show where these came from. Oops, wrong color. Now there is a general, or there is kind of a correct way to write these, and specifically what we do, let me just make that a little nicer too. When we have multiple terms, the correct order to put them in is usually the highest degree, or the highest exponent first. So it's a good rule of thumb to rewrite it with the highest exponent first. So in this case, it should be x cubed plus 1x squared, or just x squared, plus 3x. So generally speaking, this should be the correct way, or the most correct way. Now the other way is not wrong, there's just a better, more organized way to write it. But again, if you didn't, it's not entirely wrong, right? But I would challenge you to try to keep this in mind as you're solving questions or distributing the property. So what we're going to do now is we're going to look at finding a simplified expression for the perimeter and the area of the following shape. Well, perimeter we should be used to because we did that in the previous lesson. So the perimeter is equal to all the sides added up. So 7 plus 3x minus 1 plus 3x minus 1. When I go through, I look for my like terms. So I have 7s, I have -1s. They're just numbers, so they're like terms with each other. Then I have a 3x and a 3x. They're like terms because they share an x. Now I can add or collect my like terms. So 7 plus 7 is 14, -1 minus 1 is 12, 3x and 3x is 6x. So the perimeter is equal to 12 plus 6x. Or, again, you could write it better, 6x plus 12. Again, order technically doesn't matter as long as your numbers are correct, but there is a general rule of thumb that says highest degree first, then variables, then just numbers or constants. For area is slightly different because area of a rectangle is length times width. Right, hopefully you remember that. If not, I've just given it to you. So if I take my length of 7, multiply it by my width of 3x minus 1, I can now find my area. Now you may say, whoa. 7 is not the width, 7 is the length. Or sorry, 7 is not the length, 7 is the width. Look at it, it's the width. Okay? You could rewrite this or write in a different way of 3x minus 1 times 7. But because of what I know with distributive property, generally speaking, the term that I have to distribute is only a single term or a single number. Or not a single number because it could be multiple, but a single term. I've chosen to write the 7 out front. Does it really matter which way? No. In terms of distributive property, it's easier to write it the first way, but both are correct. Both still show length times width. When we're multiplying, order doesn't matter. So now I'm going to use the distributive property. 7 is going to get multiplied through to both parts. So 7 times 3x, or 7 times 3 is 21. The x carries through. And 7 times -1 is -7. There are no like terms there, so I don't need to simplify it any further because it's already simplified as much as possible. So now I have a simplified expression for the perimeter and for the area. In the next example, we're going to go through the same thing and determine a simplified expression for the area of the shape. Now, it's not a nice area or a nice shape. It is something kind of messy, but we can kind of break it up into shapes that we know. Right? I can break this up into 2 rectangles here. There's different ways you can do this, but this is one of them. Right? There's different ways you could divide it up. So if I look at the first area and the second area, I'm going to need to find the area of 2 shapes and then add them together to get the total area. So in this case, if I look at the first one, I have, again, area of the first one, it's a rectangle, length times width. Well, I know one of them is 4x plus 7, but what's the other one? I know the overall length here is 6x, but I don't want the overall length. I just want this short length here. Well, to find that, if we know the overall length is 6x, and we know that these 2 sides are the same because of the dashes, each side is the same, so that just means it's half of 6x, or 6x divided by 2. When we're dividing something like this, focus on the parts that are the same. It might help if it looks something like this. Focus on the numbers. 6 divided by 2 is 3. X gets carried along. So that means that these side lengths are 3x. So 3x and 3x. Now I have enough information to go through and find the area of each shape. So area of the first one, I'm going to say is 3x times 4x plus 7. Again, I'm putting the single term in front and the bracket or the multiple terms second to make it a little bit easier. Now I need to distribute my property. 3x times 4x. 3 times 4 is 12x. X times x is squared. Sorry, 3 times 4 is 12. X times x is x squared. And 3x times 7 is 21x. So that's the area of the first rectangle. For the second one, again, it's length times width. Here we have 3x again, multiplied by x plus 2. So slightly easier than the last one. We're still distributing our property. 3x times x is 3x squared. 3x times 2 is plus 6x. Now that I have each individual part, I'm almost done. Now that I have each individual part, I can find the total area by adding all of them together. So the area 1 plus area 2. So 12x squared plus 21x plus 3x squared plus 6x. Let me move this over so it doesn't kind of clash or interfere. I now have like terms that I can collect. Actually, let me change the color on this just to make it a little bit easier to see. I have like terms I can collect. The 12x squared and the 3x squared, the 21x and the 6x. So when I collect the like terms, I get 15x squared plus 27x. So that is the total area of the entire shape. So that is the simplified expression for the entire shape, or the area, or the total area. So that is our final answer for part A. For part B, B is now saying use that expression from A to determine the area when x equals 3. So if we know the total area is equal to 15x squared plus 27x, all this question is telling me is to substitute in. So 15 times 3 squared plus 27 times 3. 15 times 3 squared is 135 plus 27 times 3 is 81. We get 216 is the area when x equals 3 for this question. So again, as I mentioned previously in another lesson, if you weren't sure how to come up with a simplified expression, but you saw to find the area when x equals 3, you can plug x equals 3 back into each side length and then work through it to find the area. You'll still get the same area. The only reason we come up with a simplified expression is if we have a different answer for what x equals. Maybe this is a prediction or a model. We're trying to see what's the area when x equals 3. Maybe we also want to find the area when x equals 1 or 7 or 9. So rather than having to change the measurements or every measurement, I can just plug it into my simplified expression and that will give me an answer. So again, the main thing from this lesson is understanding what distributive property means and just kind of running through some of those examples, keeping in mind that you might see questions that say expand and simplify. Expand means to multiply or use that distributive property, and simplify means to collect like terms. So again, you may need to refer back to some of the previous lessons if you're a little bit unsure or you're not as confident with those processes.